Okay, let's take a look at this unit. We'll start off with section 4.1 inverse functions, and then progress to 4.2 exponential functions. Then introduce log functions and some basic properties in 4.3, and then we'll get into the three main properties of logs in 4.4, along with the change of base. And then we'll finish up with exponential and log. It says functions, but actually those are equations that we are solving for in that section. Okay, so first, our definition of a one-to-one function. Now remember, a function says for each x there's only one y. Well, a one-to-one function says for every x there is only one y, and for every y there is only one x. So it goes both directions. Now that's kind of a hard definition to work with. We got an easier definition of a one-to-one function, and what it says. Hi, Lisa. Hi. How you doing today? Oh, doing pretty good. I can't bring the grades up while I'm recording here, but let me just generally talk about it. On that pie page, the one with the picture of the pie, you have your different slices here. And if you click on that particular one for that unit, then over here it'll tell you, for example, that maybe there's 69 topics, and maybe you've 5 of them you've mastered. I'm not sure of the exact wording. And 10 of them you've learned. Does it say mastered? Okay. Now this 5 here is based upon that initial test. So it determined from that test that you already knew these topics. And these are the ones you learned, that you went through and went through the material and so forth. Now to find out how many topics that you do need to finish, there's 69 total, and for every week except for the first week, you have to finish 75% of them. So you take 75% times 69, and that gives us 51.75, or I would always round up on these. So that tells us that you need to finish a total of 52 topics for the week. Now up here, you've already mastered 5 and you learned 10. So 5 plus 10 is 15. So if you need 52 total, then you take 52 minus your 15. There should be, when you click on this, should be like a box appears over here. Oh, I see what you're saying. This should not go down here for the week. But what you'll find is, like, the first week there was 229 topics or something like that. Second week, I don't remember how many there was, but let's say there's 200. Third week it went down to, I think, like 120. And last week was what, 69 or 70 or? Yeah. Let's put 69 there. So this is just changes each week. This right here. So with that going down has nothing to do with how many you finish. That's just how many are in that chapter. Okay. Okay. I think I can go into student view without bringing up anybody's grades, or even yours. Well, I'm gonna, when I'm recording this, I put. Okay. So I'm looking at this right here, and let's see, this week's polynomial and rational functions, that little purple. So if I click the purple there, it tells me there's I remembered it incorrectly. The topics is across the top here. It says 76 topics. And this tells me how many are remaining. I swear the one I sent you, the actual number of topics is over here. But maybe I was looking at it wrong. But yeah, then you see how this says you got 13, 0, and 63. Excuse me. So then if I go through and let's see, get started, I want to do polynomial and rational functions. I don't want to do that. We'll go to learn. And polynomial and rational functions. Just looking for one I could do real quick. This one should be a quick one. Okay. Now, negative 4 and 3. So I got negative 4 and 3. And it says to write a quadratic function given those. So if I take those over, I get x plus 4. This one I get x minus 3. And if I FOIL those, I get x squared plus x minus 12. So this would be x squared plus x minus 12. And then the next one, negative 3 and negative 13. So x plus 3, x plus 13. So we'll have x squared plus 16x plus 39. And 7 and negative 2. We should have x minus 7, x plus 2. So we'll have x squared minus 5x minus 14. Okay. Let's see. Continue my path. Then if I come back to here, go home. Now, see how we had 13, 0, and 63? It's now 13 and 1 is 62. So if I want to figure out how many I've mastered, or how many I've completed, if you take the 13 plus the 1, gives you 14 divided by 76. So 14 divided by 76. And if you want it in percent, you just multiply it times 100. And that tells me I've mastered 18.42% of the topics. Does that make more sense? Yeah, I probably can't have you share your screen with that recording, but I will show this. If I go into the Learn, as soon as it comes up here, and do this drop down, then if I go back to like this first chapter here, now you see how some of these, like this one, I could go ahead and work. Ordering numbers with positive exponents. Find the nth root. Here's a set builder notation, but here's one that's locked. So you'll find that some of them are locked because it requires you to do the prereq ones before you can do those. And that's what I think you're seeing. See, if I click this, it'll tell you the topic is not available, work on your current objective. But as you go through and you unlock some of these, then you should see some of these other ones get unlocked. So now I couldn't tell you a rhyme or reason how to determine some of them. If there's only one prereq, like if I click this, I'm probably not going to be able to guess one. But sometimes if there's only one prereq, it'll take you to that prereq and say do this one first. Right, I'll readjust those for any that you finished in the past. Now, if all of them are locked on yours, that's a different issue, and let me know that. But you should see some of them unlocked where you can work on them. You're welcome. Okay. Have a good Sunday. Bye. Okay. An easier definition of one-to-one function says if you have one of the following, it is not a one-to-one function. If you have even powers, it's not a one-to-one function. If you have the absolute value, it's not a one-to-one function. If you got the plus or minus symbol, it's not a one-to-one function. Or if you got x is equal to a number or y is equal to a number. Unless there is a condition put on x. And what I mean by that is we got y is equal to x squared. Now this right here would normally not be a one-to-one function because it's got an even power. But if I put a condition on it saying where x is greater than 0, by applying that condition I'm making it a one-to-one function. Let me close this. Now identifying one-to-one functions, What they're referring to there is if you have anything that has one of these items, it's not a one-to-one function. For example, if the instructions were to determine if this is a one-to-one function, if we had x squared plus y squared is equal to 7, the fact that it has even powers means that no, this is not a one-to-one function. If you had x to the third minus y to the fifth is equal to 2, we can have odd powers, we just can't have even powers. There's no absolute value, there's no plus or minus symbol, and when I say x equals a number or y is equal to a number, that's all you have. You'd have like x equals 2 or y is equal to 5. You wouldn't have anything else. And so it doesn't have any of the prohibited items. So the answer here is yes, this would be a one-to-one function. Okay. Now we got a something called, remember the vertical line test? Said if any vertical line intersects your graph at 2 or more places, it's not a function. We have a horizontal line test. Now this just checks the one-to-one part. The vertical line test still determines if it's a function or not. The horizontal line test says if any horizontal line intersects the graph excuse me, the graph at 2 or more places, then it is not one-to-one. It might still be a function, but it's not a one-to-one part. An example of this. This is the graph of y is equal to x squared, more or less. If I draw a horizontal line here, you see it intersects at 2 or more places. So this says if it intersects at 2 or more places, it is not one-to-one. So if this was asking if it's one-to-one, then the answer would be no. On the other hand, if I was graphing y is equal to x to the third, looks like this. Draw a line here, intersects one place, here one place, here one place. No matter where I draw a horizontal line, the most it'll intersect is one place. That means that this is one-to-one. It's also a function. Okay, let me clear that off. Now, this next problem gets into determining whether two functions are inverses of each other. So we're first going to look at the graphical view on this. You have to use your imagination on this. I'm not very good at these. Okay, so this point here is -4, -2. This point here is -1, -1. And this point here is going to be 1, 3. Okay, so if I draw my lines in this manner, this is our function. Now to find the inverse and to understand, the question is, what is an inverse graphically? We're going to take a look at algebraically here in just a second. This point was -4, -2. So in blue, I'm going to put another point that's -2, -4. And that right there is -2, -4. This point here is -1, -1. So my inverse will be -1, -1. And this point here is 1, 3, so my inverse will be 3, 1. When you talk about the inverse, the point swap, the x's and y's. And so if I were to draw these, this would be my inverse. It's got this notation. Looks like f to the negative 1. This line going directly through the middle here, 45-degree angle here, 45-degree angle here. This is the line y is equal to x. And inverses are symmetric to this line. So that's how graphically you could determine if two functions are inverses of each other, is if they're symmetric, this line. Now, a very simple way to determine that is if you can take f of x, this f, if you can flip it, reflect it across the line, and it lands exactly on this graph right here, that means that they're inverses of each other. Like I said, I don't draw these very well, but if you use your imagination, if you flip that over, it's going to land exactly on that piece right there. Now let's talk about what an inverse is algebraically. Okay. Inverses of functions. And this is algebraically. F and G are inverses. Well, first, f and g are functions and are inverses if the following is true. Make this a little bit larger after I write it out. The composition of f and g is equal to x, and the composition of g and f is equal to x. So it has to be true going both directions. So if I had a problem, let me erase that. And I had f of x is equal to 3x minus 1, and g of x is equal to 1/3 x plus 1/3. And the question is whether these are inverses of each other. Well, first I find the composition of f and g, which remember is f of g. So I'm going to go to my f of x, which is 3x minus 1, and where my x was, I put in a set of parentheses. Now, whatever is inside this parentheses is automatically what goes in here. So I put g in there. But g was equal to 1/3 x plus 1/3. So I'll put that in where the g was. Now if I multiply the 3 through, 3 times 1/3 x gives us 1x, or just x. 3 times 1/3 gives us 1, minus 1. And 1 minus 1 gives us x. That's the first part. Composition of f and g should give you x. Now going the other direction, composition of g and f, that's g of f. So I'm going to take my g of x, which is 1/3 x plus 3. Where my x was, I put in a parentheses. And whatever's inside the parentheses right here is automatically what you're going to put in here, so I'll put f in there. But f is equal to 3x minus 1. Now if I multiply this through, 1/3 times 3x gives us 3 over 3x, or just 1x, or x. 1/3 times negative 1 is negative 1/3, plus 1/3. Negative 1/3 plus 1/3 cancels, gives us x, so that checks. Since both of them give us x, then the answer is yes, these are inverses of each other. That's how you determine if two functions are inverses, graphically and algebraically. Now, the third topic asks us to find the inverse of a function. So finding the inverse of a function. Let me start a new page on that. There we go. Note, f of x must be 1 to 1. If it's not 1 to 1, it doesn't have an inverse. That's why we even look at the 1 to 1 portion. Step 1, replace f of x with y. Step 2, interchange x and y, swap them. Step 3, solve for y. Step 4, replace y with our inverse notation. And step 5, if necessary, use the graph to figure out how to make the inverse 1 to 1. This is if you have an even power, if you have the absolute value, if you have the plus or minus symbol, those items that we listed earlier. Okay, let me clear this off. And let's say I have f of x is equal to 5x minus 1. And the instructions say to find the inverse. So our first step, we want to replace f of x with y. Step 2, interchange x and y, so swap them. So we got x is equal to 5y minus 1. So where the y was, you put an x. Where the x was, you put a y. Remember how we swapped our points when we looked at the graph? Same principle here, except we're doing it with variables. Now step 3 is to solve for y. So I'm going to take that negative 1, move it to the left side, and it becomes a positive 1, equals 5y. And then I'll divide both sides by 5. When I do that, these 5's are going to cancel. And you got y is equal to x plus 1 over 5. I can split this into two separate fractions if I wanted, but that form is fine. Now step 4 is replace y with your inverse notation. So we're going to have the inverse of f is equal to x plus 1 over 5. And that's our answer. Now I have quite a few more examples if you go into the particular unit, you'll see the folder for the supplemental videos that I put out there. So unfortunately, we just don't have time to show more than typically one example of these different types. Now going on to section 4.2, exponential functions. First topic is to graph an exponential function. So let me clear this off. Now I want to graph f of x is equal to 2 to the x power. Now an exponential function is where you got a function and you got a variable up in the exponent. That's what makes it an exponential function. Now to graph this, on our calculator we'll go to y equals, clear, and then we'll do 2 caret x. And then we press graph. And this would be our graph. More or less looks like this. They never just stop. This keeps going forever this way. It just skims, gets really close to the x-axis, but never touches and never crosses it. Now if I had f of x is equal to 3 to the x minus 1 power. Trick to it, when you have more than a single number or single variable in your exponent, is put parentheses around that part. So when I plug this in, I want to put parentheses around the x minus 1. So I'm going to press my y equals. Let me clear that actually. Press my y equals. Press my clear. I do 3 caret, beginning parentheses, x minus 1. You can put a closing parentheses there. If you got one of the newer TI-84s, the color-based ones, it has exponent mode. When you do the caret, it throws it up in the exponent. You don't actually need the parentheses there. And then I press graph. You'll find these are boring graphs. They kind of all look alike. So that would be our answer. One more, and then we'll look on the next topic. Some problems we may have an e. Like e to the x minus 5. On your calculator, you press your y equals, clear, and to get e, you do second ln. And that'll put your e caret beginning parentheses, and then you do your x minus 5. You don't need to put the beginning parentheses yourself because it puts it there automatically. And if I press graph, that would be our answer. Now, to get exact points, if that's what it's wanting, you can go to your table. If you do second graph, that'll take you to the table. Now, you may have a whole bunch of numbers listed here, or if you've set your calculator for ask mode, as we did earlier in the course, then it'll allow you to put numbers in. So if we put 0 in and push enter, 1 in, enter, 2 enter, 3 enter. So those are values you can use to graph. Now, if you wanted to set to ask and you didn't set it earlier in the course, if you go into your table setup, TBL SCT, so second window, and then you down arrow to independent, and you right arrow, put your flashing cursor on ask, and you press enter one time. That'll set that to ask. And then you do second mode to exit out. Now, evaluating the exponential function base e. Let's talk about that. These were graphing. Let's say I want to evaluate e to the 3.1 power to 4 decimal places. Well, make sure you're out of graph mode. Do a second mode if you're not already out. Now, to get to e, remember you do second ln. That's natural log, the ln. Then you put in 3.1. Then you push enter. Now, to 4 decimal places, we'll have 22.19. Now, I got 795. This 5 here means I'd round up, so this becomes 80, or you could just write 8. But that would be our answer. Now, that's used in compound interest, which we'll see. Now, this says use exponential functions to compute compound interest. Now, this one goes hand in hand with use exponential functions in applications. So I'm only going to show the compound interest. Let me clear that off. Now, compound interest. We have 2 formulas. We have where it does not say continuous. It might say compounded quarterly. And that's the formula. A is equal to P times 1 plus R over N to the NT power. And then we have where it does say continuous. And this is our Perp formula. A is equal to P e to the RT power. Now, A is our ending amount. P is our beginning amount. R is our rate, and it's in decimal form. T is our time, and it's in years. And N is the number of times compounded per year. That's a fancy business term. Compounded means calculated, but it's more than that. They calculate the interest, and then they take it and put it back into the account, and it compounds, it builds. It actually builds exponentially after a period of time. Of course, I guess that depends on your values you have in there. So if I'm talking about, let's say it's compounded continuously. And P is equal to 1,000. We put $1,000 in the bank account. Add 3%. So we got 3%, or in decimal, remember you move your decimal point 2 places. So that's 0.03. And we want to leave it in there for 5 years. So T is 5. Well, since it says continuously, then we'll use a Perp formula. A is equal to P e to the RT power. So P is 1,000, e to the R, which is 0.03, times, I'll put a little x there, times 5. Where people mess up in this formula is the overuse of parentheses. If I put this in, I'll do 1,000 e, so we do second ln, or natural log, and then we got 0.03 times 5. Notice that I am not putting any extra parentheses in. When you're working with the compound interest formula, compounded continuously, you don't want to put any parentheses in. And then you press enter, and 4 decimal places, 2 decimal places, sorry, 0.83. So if we invest $1,000 in a bank account, leave it for 5 years at 3%, this is how much we should have at the end. Okay, let's go on to the next section, logarithmic functions. Let me grab a drink here. I keep forgetting to check to make sure that's at the level of my nose. Otherwise you hear me breathing as I'm recording. Okay, convert between log and exponential forms. So let's talk about those forms. We have our log form. That's log base b of q is equal to p. Probably all of these have names, but one that's important, the one you should know, is what the b is called. That's your base. Now we have exponential form. That's b to the p is equal to q. Now if you had a problem that was log base 2 of x is equal to 3, and you want to change it to exponential form. Well, first thing, you have to identify your b, p, and q. So first thing we're going to look for is the b, the base. Base is a number that follows a log that's smaller that's set down. So in this case, our b is going to be 2. And then what follows that is your q. So this x is going to be our q. And then the other side of the equal is your p. So that's going to be our p. Now exponential form is b to the p is equal to q. So after we identify the b, p, and q, we're ready to plug them in. So put 2 in for the b was 3, and q is x. And that's our answer. Now if they give us 5 to the x minus 1 is equal to 2, and we want to rewrite this in the log form. Well, if we look at our exponential form, the power, the exponent, is going to be our p. So this x minus 1 here is our p. What's immediately to the left of it is our b, so the 5 is going to be our b. And then the other side of the equal is going to be our q. So then our log form, we got log base b of q is equal to p. So plug in everything we identified. B was 5, q is 2. B to the p is equal to q log base. Okay, that's right. And then p is equal to x minus 1. And that would be our answer. Now let's take a look at our special bases. First one, if you have log of something, notice on this one that there is no base. It's blank. If it says log and there's no base, then by default your base is equal to 10. This is referred to as a common log. If, though, we have natural log, or ln, this does not have a base. This is base e. Now e is 2.7 a bunch of decimal places. We saw that in the last section. We didn't really talk about what the value is equal to. Now if you're wondering, I referred to this as natural log, ln. Why isn't it NL, natural log? Well, this comes from the French, and in French that's log naturel, so that's why it's ln. Now if you have one of those and you want to convert it, for example, if I have natural log of x plus 5 is equal to 3, and I want to put it into exponential form. From the fact that it says ln, that means automatically our base is e. And then what follows a log is your q. You're going to find all these same properties and formulas work no matter what the base is. And the other side is our p. So this is p. And then our exponential form is b to the p is equal to q. Well, b was e, p was 3, and q is x plus 5. And that would be our answer. Now the next topic asks us to evaluate log expressions. Now I'm going to go ahead and work one of these problems, then I'll write the property up. Property will make it look like a complex problem, but it's a fairly simple idea. Sometimes it's not so simple getting it in the right form. If I have log base 2 of 8, and I want to simplify this without using the calculator. Well, our base is 2. So what we're going to try to do is we're going to try to rewrite the 8 as the base to a power. So I try to rewrite it as 2 to a power. Well, 8 is 2 to the third. Now, if your base matches the number that's right here, then the log and those two numbers are going to cancel. And the 3 will drop out of the exponent. And that's our answer. Now the property. This isn't one of our big 3 properties. But it says log base b of b to the p power is going to equal to p. So if your base matches whatever number follows it, then the log and those bases cancel. And our answer is the exponent. Now let me pick one that's not so easy. Let me think. 3 here and 1 over the 5th root of 3. First off, nowhere in this chapter do we want radicals. So first thing I'm going to do is rewrite this. This becomes 3 to the 1/5 power. Now we had a property from intermediate algebra said that you can move something opposite of where it's at in a fraction. This 3 to the 1/5 I can move up on top. And when you do that, the sign of the exponent changes. So it goes from a 3 to the positive 1/5 to the 3 to the negative 1/5. Now after I move that up on top, notice that these 3's match. So log into those 3's is going to cancel. And our negative 1/5 comes out of the exponent. and that's our answer. Again, fairly simple idea, but not always simple to get in the correct form. Now that was actually apply the basic properties of logs also. Now to graph a log function. We're not going to look at the applications here, just in the interest of time. If I wanted to graph y is equal to natural log of x plus 5. Now this one I can type directly into my calculator. I have to go to graph mode, so I press y equals, press clear. We got a natural log ln, so I'll push my ln button, and then x plus 5, and then graph. So then our answer looks like this. These graphs are wrong on the graphing calculator. They never just stop. It keeps going down forever. It's actually symmetric to the line y is equal to x for the exponential functions, which we know never stop. But the calculator gets confused. The next point is so far down, it thinks that the graph is done, so that's why it graphs it this way. Now, if you have log, you can just graph it. But if you got another base, like you got 3, here we got an issue. Because we have 2 buttons on our calculator. We have the log button right here. That's base 10. That's common log. We have the ln button. That's base e. That's our natural log. We don't have a base 3 button. Because you can have any number here. You could have 5, you could have 7, 11, 201. So we would actually need an infinite number of buttons to handle all the different bases. What you have to do is you have to use a change of base. And change of base allows us to rewrite this as log of x minus 1 over log of 3. So I'm rewriting it with base 10, common log. Now how it always works is whatever follows your log, that always goes up on top. And whatever your base is, this 3, is always what goes down below. Now you could rewrite it that way, or you could even use natural log. So we could rewrite that as natural log of x minus 1 over natural log of 3. Change of base actually says you can rewrite it as any base, base 5, base 12. The only 2 that make sense for graphing purposes in this class on the calculator is either log, which is base 10, or natural log, which is base e. Now I'm going to graph this. So I'll go to y equals, clear, and I push my log button. Then I got x minus 1, closing parentheses, divided by my log button, and 3. And you can put a closing parentheses at the very end there. You don't need them at the very end. You do need them if they're in the middle of the problem, like after that x minus 1. And then graph. And yet again, it gives us the wrong graph. But we know they never just stop. So, not that I can draw real smooth. It looks something like that. Just keeps going down forever. Now, next section is properties of logs. So let me grab another drink. These are the 3 main properties of logs: product, quotient, and power properties. We looked at some other log properties that are minor, like change of base and so forth, but these are the 3 main ones. If you have log of something plus log of something, addition becomes multiplication. If you have log of something minus log of something, well, subtraction becomes division. And if you have a number out in front of your log, although technically it doesn't have to be strictly a number, you can have a variable, you can take that number, take whatever's in front of your log, and put as your power. Those are our three main ones. The first one is, you can guess what it is. Product, m times n, that's product property. This is a quotient property, m divided by n. And this is a power property. Now I said log of something plus log of something. That's pretty vague, but it really is as vague as what I just indicated there. It doesn't matter what you have, as long as they're added together here, or multiplied, or subtracted, or divided, or this form. We're going to find you can go either direction on these. Okay, so let's take a look at an example. Say we got log x squared y to the third over z to the fifth. Now we want to use our properties to rewrite this such that it's split up. It's no longer a single log, but it's multiple logs. You always have to ask yourself what's the main thing that's happening in the problem, besides log. So ignoring the log, we have the second power, we have the third power, we have the fifth power. We got multiplication up on top, and we got one division. Now when I say the main thing is happening, I'm talking about what would use everything in your problem except for that log. Well, that'd be division, because that'd be the top part divided by the bottom part. So it'd use everything over here. Well, division from property 2, we can rewrite as subtraction. So this becomes log x squared y to the third minus log z to the fifth. Now our first log here, we have a second power, we got a third power, we got multiplication. Now again, you're asking yourself what's the main thing that's happening, and it's not the second power, because not everything's being raised to the second power. The main operation would be multiplication, because we'd have x squared times y to the third. That would use everything here. Well, multiplication from property 1 becomes addition. So this will become log x squared plus log y to the third minus log z to the fifth. Now there's only one thing left. All of these have powers on them. And we can take the power and put it out in front of the log. So that becomes 2 log x plus 3 log y minus 5 log z. Now our goal on these, if we can get it that way, is to get a single variable with a log in front of it. Well, x with a single log in front of it, y with a single log in front of it, z with a single log in front of it. So that's in the right form. Now sometimes you may get the form log x plus 1 minus log x, something like this, and you don't have a single variable here, but that's as good as it gets because we don't have any property that allows us to break that apart. Now this direction is used a lot in calculus. This is where you take a well, that's nice. Let me start that over. There we go. That's curious. Usually when I'm recording, it won't actually do that. Wife's killing me with the heat in this house. I'm going to open my window a little bit more. I get some air coming in. Okay. Now this is using calculus. This is where, if you're finding something called a derivative, finding a derivative of this would be kind of complex. But finding a derivative of this would not be too bad. Now let me clear this off. And we can have problems going the other direction. 3 log x minus 7 log y plus 4 log z. Now, the trick here is you cannot use properties 1 and 2 while there's any number in front of the log. Well, we don't have any we have numbers in front of a log here, so we have to use property 3. It says if you have a number in front of your log, you put it as your power. So this becomes log x to the third minus log y to the 7th plus log z to the 4th. Now, other than that, for properties 1 and 2, you use these just with your order of operations. You apply them as you encounter from left to right. Our first addition and subtraction from left to right is right here. And subtraction becomes division. So this will become log x to the third over y to the 7th plus log z to the 4th. We then do the next addition and subtraction from left to right. Here we got log of something plus log of something. Addition becomes multiplication. So we're going to have log of x to the third, y to the 7th, times z to the 4th. So up on top we're going to have x to the third, z to the 4th, and down below we'll have y to the 7th. And that would be our answer. Now is our goal. Our goal was to get a single log. When I say a single log, you want to simply say log of something. Nothing in front of log, just log of something. Okay, so we covered those. Change of base we talked about in the previous section. So let's go down to exponential and logarithmic equations. Now, first topic says solve exponential equations. We're going to first talk about the equality of exponents. Very simple idea, but not very simple to get in the right form sometimes. This says if you got b to the p power is equal to b to the q power. B's are typically numbers. Those are our bases. Then you can cross out the bases, cross out the b's, and set the exponents equal to each other. So you'd have p is equal to q. For example, if I had 2 to the x is equal to 16. What we do is we start with our large number, which is 16. We try to rewrite it as the other number to a power. Well, 16 would be 2 to the 4th. Now, the equality of exponents says, since they both are 2 to a power, I can cross the 2's out and set the exponents equal to each other. So that'd give us x equals 4. Like I say, very simple idea. These both have the same number. You just cross them off, set the exponents equal to each other. But if I had this right here, 8 to the x minus 1 equals 16. Well, if I start with the larger number, start with 16, there's no way I can rewrite that as 8 to a power. 8 to the first is 8. 8 squared is 64, so it doesn't work. So what I have to do this time is start with both sides and think of how I can rewrite each side as the same number to a power. Well, 8 I can rewrite as 2 to the third. And 16 I can rewrite as 2 to the 4th. Now notice when I put the 3 up here in the exponent, it already had an exponent, so I had to put parentheses around the exponent that was already there. Now since they're both 2 to the power, those 2's cancel. And I got 3 times x minus 1 is equal to 4. I set the exponents equal to each other. And solve this. 3 times x is 3x. 3 times negative 1 is negative 3. Is equal to 4. Get everything with an x on one side, numbers on the other side. So I take that 3 over. Becomes a positive 3. Which gives us 7. And then you divide both sides by 3. And you get x is equal to 7/3. And that's our answer. You may have to rewrite a radical in fractional power form in order to work it. For example, if I had 2 to the x is equal to the square root, or cube root, let's say, of 2. We don't want radicals anywhere in this chapter. So cube root of 2 is 2 to the 1/3 power. Now since they're both 2 to the power, the 2's would cancel. And I apologize for the noise. You'd think I live right next to the train yard the way it's going. And between the trains and then the church over there playing their melody forever. So that would give us our answer. Now let's take a look at another problem. Three to the x is equal to 5. These were exponential equations because you got variables up in the exponent. Now there's no way I can rewrite 5 as 3 to a power. There's no way I can focus on both sides rewriting both of them as the same number to a power. So it doesn't work. Well, solving exponential equations. Our first step is to get the part with the variable in the exponent by itself on one side of the equals. Step 2 is to take ln of both sides, natural log. Step 3 is to use properties of logs to get the variable out of the exponent. And then step 4 is to solve for x. Okay, so step 1. Get the part of the variable in the exponent by itself on one side of the equals. This is the part of the variable in the exponent. It's by itself. There's nothing in front of it. There's nothing after it. We simply have 3 to a power. Step 2. Take natural log of both sides. So we're going to have natural log of 3 to the x is equal to natural log of 5. Step 3. Use properties of logs to get a variable out of the exponent. Well, from the previous section, we said if you have log of something to a power, you can take the power and put it out in front of the log. So this becomes x natural log of 3 is equal to natural log of 5. And then step 4 is to solve for x. Well, it's kind of bizarre looking, but natural log of 3 is just a number. So we're going to divide both sides by natural log of 3. Now when you do that, these natural log of 3's cancel. And we got x is equal to natural log of 5 over natural log of 3. Now you cannot cancel the ln's. You can't say that's equal to 5/3 because the natural logs actually transform those numbers. If you want to put it in decimal form, you just plug it in your calculator at that point. Now if I had e to the x minus 3 minus 1 equals 5. And step 1. Get the part of the variable in the exponent by itself on one side. It's not this e to this power is not by itself because there's a minus 1 here. So I could add 1 to both sides or simply take that negative 1 to the right side. You take that over, it becomes a positive 1. Then 5 plus 1, 6. Step 2. Take natural log of both sides. So you got natural log of e to the x minus 3 is equal to natural log of 6. Now what you're going to find, whenever you have natural log and e, they're going to cancel each other. So that gives us x minus 3 is equal to natural log of 6. You like the problems with the e because it always works out that way. And now we want to solve for x. I take that negative 3 to the right side, and we got x is equal to 3 plus natural log of 6. And that's our answer. So let me clear that off. Now we'll take a look at log equations. log base 2 of x minus 1 is equal to 3. Okay. Solving log equations. Our first step is to get everything with a log on one side, numbers or constant terms on the other side. Step 2, use properties of logs to get a properties of logs / basic algebra to get a single log. Step 3, use the definition of a log to rewrite in exponential form. This is the b to the p power is equal to q definition. Step 4 is solve for x. And step 5 is to semi-check your answer. And we'll talk more about that. But we don't need to fully check it. Okay, step 1. Get everything with the log on one side, numbers on the other side. That's done. Everything with the logs over here and our numbers over here. Step 2. Use properties of logs, basic algebra to get a single log. We got a single log. That's done. We got a log of something. That's what it means to get a single log. You should just have a log of something. Nothing in front of it, nothing after it. Step 3, use the definition of log to rewrite an exponential form. Remember, the number that follows your log, the smaller is your base. So b is 2. This right here is going to be our q. And the other side of the equal is going to be our p. Now our exponential form is b to the p is equal to q. So we plug in what we identified. We said b was 2, we said p was 3, and we said q is x minus 1. And then step 4 is to solve for x. Well, first off, 2 to the third is 8. Equals x minus 1. And I take negative 1 over, it becomes a positive 1. And I get x equals 9, maybe. Remember what I said? I said you have to check your answer. If I plug 9 back in, 9 minus 1 is 8. What we can't have is we can't have log of 0 or log of a negative number. So that's all we're checking. 9 minus 1 is not 0 and it's not negative. So that's our answer. Now I'm not going to work these all the way through. I just want to talk about the setup. Some of these I couldn't make up on my head and have them work out nice. So now first step, get everything with a log on one side, numbers on the other side. That's done. Step 2, use properties logs to get a single log. Well, we have log of something plus log of something. If you remember from the previous section, you can rewrite addition as multiplication. So this becomes log base 3 of x times x minus 2 is equal to 5. Or log base 3 of x squared minus 2x is equal to 5. Now just to show the next step, even though I'm not going to take it any further than that, we would identify our b, p, and q. So the 3 is our b, then what follows that is our q, and then the other side of the equals is our p. And our exponential form says we got b to the p is equal to q. So we'll plug in everything we identified. b was 3, p is 5, and q is x squared minus 2x. And then you'd solve it down from there. You'd use, in this case, it wouldn't factor, I'm pretty sure since I made the problem up, but you would use quadratic formula. Now that covers log equations, and that's really where I wanted to get to today. So let me go ahead and stop the recording.